Hey everyone, welcome back to another video by Camroom 5. In today's video, we're going to start and revise the various kinds of van der Waal forces which exists between particles. Now we're going to also consider the forces that might exist between particles which are not covalent. So if I'm not wrong, we have various kinds of structures that exist. First, we have these giant ionic lattice. Then if I'm not wrong, we have a thing called metallic lattice. And then we have a thing known as the covalent structures, right? When we talk about the covalent bonds or covalent structures, we have two more categories. Within covalent, the first category we have is, let me write it first. Yeah. So within covalent, the first category we have is simple molecules. And then we also have giant covalent molecules. The arrow is opposite, but that's okay. So we have got giant covalent molecules. Ionic lattices have electrostatic forces between oppositely charged ions. Metallic lattices have the same electrostatic forces. This time it is between positive ions and sea of electrons. When I talk about giant covalent or simple covalent, then it becomes trickier. In giant covalent, it's always about many strong covalent bonds between atoms. For example, if I were talking about diamond or graphite or silica, this is what my phrase should have been. And then when I talk about simple molecules, then things become trickier. So when I talk about simple covalent molecules, then I have a lot of categories. Simple molecules, we are aware of the fact that those molecules could be one of those two things. Those molecules could be non-polar or those molecules could be polar, right? Non-polar by definition means zero electronegativity difference, and polar means there is electronegativity difference. When I'm talking about non-polar molecules, I generally talk about a thing called ID-ID forces, as I've mentioned in the last video. But when I'm talking about polar molecules, I could be talking about PD-PD forces, or I could be talking about hydrogen bonds depending on those molecules. To understand this even more deeply, let's go for an example and with a set of molecules. I've got multiple molecules over here, few are ionic, few are covalent, few are giant covalent. So for example, if I were developing a comparison between a metallic lattice and let's suppose S8 molecule, which we all can know is a simple covalent molecule. It's a simple molecule. If I were to draw a comparison between a metallic lattice and a simple covalent molecule like this, then my answer should involve reference to strong electrostatic attraction between metallic lattice and sea of electrons, and with reference to S8, I might end up saying that it's a simple molecule with weak intermolecular forces. Because when it's a comparison between a metallic lattice and a simple molecule, I don't have to talk about ID-ID or PD-PD forces because those forces are just within those simple molecules, right? Those forces are just within simple molecules. So why should I talk about them when the other comparison is not even a simple molecule, it's a metallic? Similarly, If I were drawing a comparison this time between a giant covalent structure and a simple molecule, I would talk one sentence about many strong covalent bonds between giant covalent structure within giant covalent structure, and I would just mention weak intermolecular forces in the simple molecule of my acid. If I were drawing a comparison between giant ionic lattice and a simple molecule, I will very clearly say strong electrostatic attraction between opposite ions in giant ionic lattice. And with referring to acid, I would just say it's a simple covalent molecule, it's a simple molecule with weak intermolecular forces, which are easy to overcome with less heat energy. Whether it's acid or Cl2 or P4 or HCl, these are all simple covalent molecules at the end of the day. So my comparison would with metallic or with giant covalent or with giant ionic would look exactly the same way. Things become interesting if the comparison is between simple covalent molecules like acid and Cl2, or like acid and P4, or like acid and HCl, things like these. So if the comparison is between various simple covalent molecules like these, or let me put it into a different color, let's suppose like these, only then I would talk about specific categories of intermolecular forces. So if the comparison is this time between S8 and Cl2, like this, then I would talk about that both are simple covalent structures. And then I would talk about that S8 has more electrons per molecule than Cl2. So S8 has stronger ID forces, because this time they are both simple covalent molecules. If the comparison was between P4 and Cl2, again I would notice that both are simple covalent molecules. So I would say P4 has more electrons per molecule than Cl2 molecule, or Cl2, let me write it, molecule. So P4 has stronger ID forces because they all are non-polar simple covalent molecules. They are all non-polar simple covalent molecules. So my answer will involve ID references or PD references only if they are simple covalent molecules. Otherwise, if they are giant ionic or metallic or covalent, then why should I talk about specific ID? I can just say intermolecular. But if it is between simple covalent, then you specify ID or PD or strength of ID or strength of PD. Now let me build another example. Let me give you another example. This time, I am comparing another two simple covalent molecules, but this time I'm comparing my simple covalent molecule. Let's say I'm comparing Cl2 with NH3. So Cl2 is a simple covalent molecule, like I know it's a simple molecule. Ammonia is also a simple molecule. This time I will have to specify the kind of intermolecular force. One of them is non-polar, chlorine is non-polar, ammonia is polar. So this time don't talk about ID. Like in one category it would be ID, but in another it would be a kind of PD force which happens in ammonia. So this time I would say that chlorine is a non-polar molecule with weak ID-ID forces. With weak ID-ID forces. But ammonia has hydrogen bonds. You know, hydrogen bonds are there present when hydrogen is bonded to a very electronegative atom of oxygen or nitrogen or fluorine. So you can see hydrogen bonds would be here. I don't know why it does it here. So chlorine is a non-polar molecule with weak ID-ID forces, but ammonia has hydrogen bonds between its molecules. And then you can talk about more heat energy is required to overcome the hydrogen bonds, but less heat energy is required to overcome the weak ID-ID forces. You compare another sentence about heat energy. Let me give you one more example. Let me give you another example between, let's suppose I'm giving an example between chlorine and this HCl. This time both are again simple covalent molecules, right? HCl is also a simple molecule, and if I'm not wrong, chlorine is also a simple covalent molecule. But again, HCl is a polar molecule. So this time you would also talk about specific category. You would say fluorine is a non-polar simple molecule with weaker ID-ID forces, but HCl is a polar molecule with PD-PD forces which are stronger and require more heat energy. So the concept of today's video was developing an understanding of the structure before you comment on the forces which govern the melting point and boiling point. If your forces are compared between metallic and simple, or metallic and giant covalent, or ionic and simple, then you don't talk about specific ID-ID forces or PD-PD forces. You talk about ID-ID and PD-PD only when it's a comparison between simple covalent molecules. And then you get into the specifics of the forces. I hope this idea was clear for you guys. Thanks.